Hello, everyone, and welcome to The Explainer. I'm so excited to jump into today's topic with you, mastering coordinate geometry. Think of this branch of math like a giant, ever-expanding toolkit. It's this beautifully logical system that lets us literally map the mathematical world. We're seamlessly translating visual shapes and lines into algebra, and vice versa. We'll start from the absolute basics of mathematical navigation and build up to solving some seriously complex geometric puzzles together. It's going to be a fantastic journey, so let's get right into it.
Okay, let's dive into this. Here's our roadmap for this explainer. We're going to start with the Cartesian coordinate system and navigating the four quadrants. Then we'll master the distance formula and the midpoint formula before jumping into checking points for collinearity and finally solving for shapes and area.
So, part one, the Cartesian coordinate system, the absolute blueprint of geometry. To really get this map, we actually have to rewind all the way back to 1637. That's when the brilliant French mathematician René Descartes introduced the Cartesian system. His idea was kind of revolutionary, but so simple. Create a standard way to describe the absolute precise position of any point on a flat, two-dimensional plane. That one single concept, it literally gave birth to the entire branch of coordinate geometry we use today.
Now let's look at how this map is actually built. Think about how your phone's GPS works. You need intersecting roads to pinpoint a location, right? Well, in our Cartesian plane, we pinpoint a point's position using two fixed, perfectly perpendicular lines called coordinate axes. You've got the horizontal line, that's our x-axis. Cutting straight through it is the vertical line, the y-axis. These two main highways intersect at one critical junction, right in the dead center, and we call that point the origin.
So the crucial thing here is how we actually write down a location on this grid. We use an exact mathematical address called an ordered pair, and it's written in parentheses as a, b. That first number, a, is the x-coordinate, or if you want to use the fancy mathematical term, the abscissa. It just tells you your horizontal distance from the vertical y-axis. The second number, b, is the y-coordinate, or the ordinate, which is your vertical distance from the horizontal x-axis. And hey, order matters entirely here. Going to point 2, 3 is a completely different destination than 3, 2. You definitely don't want to mix those up. Moving on to part 2, navigating the four quadrants and understanding the convention of signs. Because our axes extend infinitely in both positive and negative directions, they chop our plane up into 4 distinct neighborhoods, or quadrants. As you move around, the positive and negative directions totally dictate the signs of any point inside them. Quadrant 1 is the all-positive neighborhood, so the signs are plus, plus. Move over to quadrant 2 and the x values go negative, so we get minus plus. Down in quadrant 3, everything is negative, minus minus. And finally in quadrant 4, x is positive again, but y stays negative, giving us plus minus. Basically, just by looking at the signs of an ordered pair, you immediately know exactly which neighborhood you're parked in. But wait, what if you aren't in a neighborhood at all? What if you're parked right on the highway itself? Well, if a point sits exactly on the x-axis, its vertical distance is just 0. So its y-coordinate is always 0. We write that as x, 0. Likewise, any point chilling directly on the y-axis has an x-coordinate of 0, written as 0, y. These points don't actually belong to any quadrant. And sitting right at the absolute center of the whole shebang is our origin, represented by the ordered pair 0, 0. All right, part 3, mastering the distance formula. This is our mathematical measuring tape. Let me introduce you to the ultimate tool for finding the exact length between any 2 points on our Cartesian map without ever having to pull out a physical ruler. It's the distance formula. It tells us that the distance between point A and point B is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And if you look closely at the math here, you'll realize this is really just a brilliant application of the Pythagorean theorem. We're basically calculating the hypotenuse of an invisible right triangle formed by our 2 points. And remember, if you already know the final distance but you're missing one of the specific coordinates, you can just use some basic algebra to work backward and solve for that unknown. Now, here's a really fantastic little shortcut. What if you want to find the distance of a point, let's call it P, from the exact center of our map, the origin? Well, because the coordinates of the origin are just 0, 0, our giant distance formula gets a massive time-saving upgrade. All those extra subtraction terms just drop away, and the distance simplifies neatly to just the square root of x squared plus y squared. It makes calculating a distance from the city center an absolute breeze.
Which brings us to part 4, the midpoint formula explained, finding the exact center.
You know, what's beautifully intuitive about this next piece of math is that if you have a line segment with two endpoints and you want to find the precise middle coordinate, point M, you don't need any complicated square roots. You're literally just calculating an average. You add the two x coordinates together and divide by 2. Then you add the two y coordinates together and divide by 2. It's elegant, it's straightforward, and it perfectly pinpoints the exact balance point on any line segment.
Next up, part 5. Checking points for collinearity, how we prove lines are perfectly straight.
So, when 3 points lie on the exact same straight line, we call them collinear. But how do we actually prove that mathematically? We break the heavy lifting down into a simple logical sequence. First, we grab our distance formula and measure the length between point A and point B. Second, we measure from B to C. Third, we measure the total stretch from A all the way over to C. Finally, it's the moment of truth. We check if the sum of the two smaller segments perfectly equals the total distance. If AB plus BC equals AC, bingo, you've flawlessly proven collinearity.
And finally, part 6, solving for shapes and area, building and analyzing structures.
Before we start measuring anything complex, we absolutely have to memorize our foundational shape properties. Why? Because these are our target numbers. Like if you measure 4 points and find all 4 outer sides are equal, you might instantly think, oh, I have a square. But actually, hold on a second. A rhombus also has 4 equal sides. The crucial distinguishing factor is the diagonals. A square has equal diagonals, but a rhombus doesn't. It's the same deal with a rectangle and a parallelogram. They both have equal opposite sides, but only the rectangle has perfectly equal diagonals cutting across the center. This means that proving a shape is a square, a rectangle, or a rhombus on a coordinate plane is definitely not guesswork. It's a rigorous, meticulous process of data collection. First, you calculate the lengths of all 4 outer boundaries using our trusty distance formula. Second, you calculate the lengths of both internal diagonals. Finally, you take those 6 calculated lengths and match them against the exact properties we just went over. Sure, it takes a little patience, but it guarantees you'll identify the geometry perfectly, every single time.
To wrap up our toolkit, once we've identified our shapes and found the lengths of their sides, calculating their physical footprint, their area, is super straightforward. If your calculations revealed a rectangle, the area is simply the length times the breadth. If we mapped out a right-angled triangle, its area is 1/2 multiplied by the base multiplied by the height. You just plug the numbers you already gathered right from your distance formula into these classic area formulas, and boom, you have your final answer. Look at what we've accomplished today. We started with a totally blank page and built a complete system for plotting points, measuring exact distances, finding perfect centers, and rigorously proving 2D shapes. But before we wrap up, I want to leave you with a thought to chew on. We've completely mastered mapping on a flat mathematical plane using an x and y axis. But what do you think happens to our trusty distance and midpoint formulas when we introduce a new, depth-defining z-axis to map the 3-dimensional real world around us? It's a game changer for sure. I highly encourage you to keep exploring, keep mapping, and keep that curiosity alive. Thanks so much for joining me today on The Explainer.